In the last lecture, we have seen what is random variable. So, random variable is a measurable function for our course. So, we take mathematical model of random variable. We have seen 3 examples. So, now today I would proceed further to talk about what is the sigma algebra generated by random variables and other issues. Okay. So, sigma algebra generated by random variable, when we say that, we first have a map. Okay. So, the map is x, which is coming from omega to r, and then sigma x is the smallest sigma algebra on omega, such that x is measurable with respect to the measurable space omega sigma x. Okay. So, the basic reason of existence of that sigma algebra is that the collection of sigma algebras under which x is measurable is non-empty, as the power set of omega is already in that collection, and then arbitrary intersection of sigma algebras is still a sigma algebra. So, from that one can get smallest sigma algebra for which x is still measurable map. Okay, so let us see a quick example. If we take omega as closed interval 0 1, then the following the integral function of 0 to half, which we earlier have seen as an example of Bernoulli trial. So, for that, the sigma algebra generated corresponding to this particular map would contain exactly 4 sets: the empty set, the full set, and the set 0 to half, and another is open half closed one. Okay. So, how do you get it? You just take inverse of 1 with respect to the map x, and then you get closed 0 to half. Okay. So, 1 is a singleton set and singleton set is a Borel set. So, inverse image of that should be measurable if my function x is measurable. So, I must have closed 0 to half inside the sigma algebra under which x should be measurable. Okay. And that justifies the complement, that is half open 1 closed, should also be inside that collection. Okay. So, next we also like to recall that if y is a random variable which is measurable with respect to sigma x, then y is constant on these intervals 0 to half and half to 1. Okay. Or in other words, you can say that y is left continuous step function with only discontinuity at half. Okay. So, here we cannot just derive any particular value of y. However, we just can derive this much, that y should be constant on these sub intervals. So, any such function y would be measurable with respect to sigma x. Now, we see what happens if we have a collection of random variables instead of a single random variable. Okay. For that, so say we consider a sequence xn of random variables. Here sigma of sigma xn denotes the smallest sigma algebra on omega, so that each of xn is measurable. Okay. One might not need to consider only countable collection, one can take arbitrary I mean large collection also. Okay. So, here we introduce what we call as filtration. We need this term throughout the course. So, this is an important concept. Let omega f be a measurable space, a non-decreasing sequence of subsigma algebra of f. Okay. We write down f subscript n, and this is a family, countable family of sigma algebras, is called a filtration of f if these are non-decreasing, correct. So, like fm is a subsigma algebra of fn, okay, for all m less than or equals to n. Now, this is a description for countably many sub-sigma algebras, so countable filtration. However, for continuous time case, one needs an uncountable family of sigma algebras. So, for continuous time case, the family of non-decreasing sub-sigma algebras f subscript t, here t we take from closed interval to infinity, of f is a filtration of f. Okay, so, we make a remark that indeed any partial order index set can be used to define a filtration, because we are not using any algebraic structure of the index set, correct. We just need that, I mean m less than or equals to n, etc. So, just order of the set p poset is sufficient. Now, let us see some example of increasing family of sigma algebra. So, here it is a trivial example that on the left hand side you have only trivial sigma algebra on the say closed interval 0 1, and on the right hand side you have the power set of closed 0 1, set of all subset of closed 0 1, and in between the sigma algebra what I have seen in the last slide appears, that which contains empty set and this half interval and the remaining and the full. Okay. However, this is not a infinite sequence of sigma algebras. Next example, we see that we take independent and identically distributed random variables xn, which are Bernoulli. Bernoulli in the sense that okay, they are uniformly distributed on binary values 0 and 1. So, that means it takes value 0 with a probability half and 1 probability half. Okay. Then if we define f subscript n as sigma algebra generated by x1, x2, etc. up to n, then we are going to get an increasing family of sigma algebras, because every time I am going to add one more random variables, and then we are requiring fn such that all of x1 to xn should be measurable with respect to that. So, you are asking more and more functions to be measurable with respect to the sigma algebra. So, the sigma algebra is non-decreasing. We cannot say it is strictly increasing, because one can of course choose for some other cases like all x is same, but here one cannot because it is independent. So, all x are not same. So, one would actually get increasing family of sigma algebras in this case. Okay, so these are examples. We call this Fn filtration due to the above definition. Okay, now we introduce what we call filtered probability space. So, here we denote this combination where omega is the non-empty set, f is the sigma algebra, and Fn is the filtration, that means the family of sub-sigma algebras, and p is the measure which is defined on omega f. Okay. So, this whole collection together we are going to call as a filtered probability space. When we are dealing with continuous time case, okay, then we would rather consider omega f f t. Okay. So, when I write down t, small t here, we would always mean that we are talking about close 0 to infinity as the index set. Okay. So, most of the time we are not going to write down that explicitly, okay, now onward, and soon we would actually talk everything in this setting only, not countable setting. Okay. So, countable setting is discussed here just to get the first intuitive understanding. Now, stochastic process, what is stochastic process? It is a family of random variables. So, given a measurable space omega f, if we have a family of measurable maps, that means random variable from omega to r, then x is a stochastic process. So, here we are restricting ourselves to only real valued random variables. Okay. There is no problem, one can actually take x as a stochastic process, y as a stochastic process, and can take order pairs x comma y. That would be again a stochastic process in 2-dimensional space, okay, R2, and then one can add 1 by 1, etc. So, then one can get actually using the same setting with no additional difficulty stochastic process on any Euclidean finite dimensional Euclidean space. Okay. However, that is not only the end of this topic. One can actually take stochastic process on higher dimensional spaces also, but for our purpose it is sufficient to talk about only finite dimensional space. So, stochastic process on the finite dimensional space, and therefore, all my definitions would be only for R real valued to define, and whenever we need Euclidean space valued stochastic process, that would be understood immediately. Okay. Now, adapted process. So, if xt is ft measurable for all t, then xt is called ft adapted. So, adapted process. So, this name we should remember, because we are going to use this heavily throughout the course. Okay. I mean, when you say xt is ft measurable for all t, then xt is called ft adapted. I mean, here we mean that not the particular random variable xt at time t, but we mean that the process x throughout the timeline, and ft is like the not a particular sigma algebra, but the collection of sigma algebra, the whole filtration. So, the better notation is actually putting a curly bracket on both the sides here and here. Okay. Usual filtration due to a stochastic process is a very important notion when nothing is mentioned. So, in a context when nothing is mentioned about the filtration, just one is talking only about the random process, then a default filtration is always there. Okay. So, what is the default filtration? So, let us describe it. So, first default thing is that you just define a GT which is sigma algebra generated by xu, where u is from 0 to t, close 0 to t. Okay. So, that GT would of course form a filtration. However, for some applications and for proving some interesting theorems, we need some more property of a filtration. Okay. What are these? One of these is right continuity, and another thing is the completeness. Okay. So, so these are the notions which I am not presenting separately, but in a together manner. So, consider that N is a set of all null sets. What do I mean? That subsets of zero measure sets. Okay. Say subset of zero measure subsets, zero measure sets of the filtration GT. Okay. So, actually subsets of not GT, but for F. Okay. All null subsets of F, then Ft defined by sigma algebra generated by N and G u u greater than T, and then intersection. What does it mean? That I have GT, but I do not consider that. I consider all GU which is where u is more than T. So, all sub sigma algebras which is after GT. Okay, and take intersection of all these. So, like coming from the right hand side, and as I have told that arbitrary intersection of sigma algebras is a sigma algebra. So, this intersection of G u u greater than T is itself a sigma algebra, and if you change your T, increase your T, that would also increase. So, it is a filtration. So, this part itself becomes a right continuous filtration, but we also augment some more sets. N is a set of all null sets. Yes, any question?
Is set of all null set of L.
F. Yes, so this is a mistake here. I should have written F here. Okay. Otherwise, it looks like N, it depends on T. Okay, so it's not. So F, and then if you take union of a sigma algebra with a set, you might not, I mean set means with a collection of subsets, you might not get a sigma algebra at the end. So, we must talk about the sigma algebra generated by this collection. Okay. So, then you are assured to have a family of sigma algebras which is increasing and which is right continuous and which is complete in the sense that every subset of zero measure set is measurable here. Okay. So, this particular choice of filtration is canonical, and we call this usual filtration of the given process X. Okay. Or we sometimes say that let Ft be the sigma algebra generated by X satisfying usual hypothesis. Okay. So, there are many different ways to describe or to specify this filtration, okay, within the text. Okay. So, there are many definitions in this slide, because this is the introductory part of the course, and the aim is to have all those together at one place, so that it is easy to refer. So, there is a notion of modification of stochastic processes. Okay. So, if you imagine you have two stochastic processes x and y, and they are such that for each and every t they are equal with probability 1. Okay. X t is equal to y t, and that happens with probability 1, and that happens for all t. Okay. Then what do you call? You would call that, okay, x and y are modification of each other. One also says that x and y are version of each other. Okay. X is a version of y, y is a version of x, etc. So, this actually is an equivalent relation, correct. If x is modification of y, y is modification of z, then x is also modification of z. Okay, it has transitivity, flexibility, everything, and symmetry. Okay. However, there is another stronger notion, which is that x and y would be called indistinguishable if x and y, the pathwise they match with probability 1. Why pathwise I am saying? Because this relation is true for all t. So, for every omega path, every sample point, the process would result in a full path, correct, for every t, and then that path of x and another path coming from y for the same event, same sample, they would coincide, and that coincidence would be observed with probability 1. Okay. Now, what is the difference between that? That can be explained with one small trivial example. Consider omega to be close 0 to infinity open, and if Borel sigma algebra on omega, p is atomless. Okay. So, that means for any given point in that, p of that singleton is 0. Okay. So, there are plenty of such atomless measures, you know. Okay. So, that much you just assume, and then define one stochastic process in the following manner for each omega, okay, fixed omega, and then you are defining the how it moves as t grows. So, it is 0 every time, only when t is equal to omega, then it is 1, because my omega is now, like time like domain, close 0 to infinity. Okay. So, I can always talk about it. So, wherever my omega is chosen for capital omega, and then x t would be 0 before it is omega, and when at omega it is 1, and then again it becomes 0. Okay. So, at the end, what are you going to get? You are going to get a stochastic process which is 0 for every time, only at omega it is 1. So, it is discontinuous function, the path is discontinuous. So, if you ask that what is the probability that you are going to see that this t to x t, this map is continuous, okay, that probability is 0, because nowhere it is like that. Okay. However, if we choose another process y, where you do not have that perturbation, it is 0 all the time. Okay. And then you ask for which omega x t and y t are same. Okay. So, you fix one t, okay, any time t, and ask for what omegas, this x t and y t would be the same. We would see for all omegas which is not equals to t, both are 0. So, they coincide. Okay. So, this is true for all omega except t. So, the measure would be 1 minus measure of singleton t, but singleton t has 0 measure because p is atomless. So, this probability is 1 for all t. Okay. So, this proves that this example of x and y, okay, so these are modification to each other. However, if we ask that, okay, pathways are the same, no, pathways are, they are never same. So, they are surely not indistinguishable. Okay. So, this example actually illustrates the difference between these two notions. Okay. We are talking about now measurability of stochastic processes. Okay. So, what do we mean by a stochastic process is measurable? Okay. So, here We must notice it, this is a very important thing, that a stochastic process is actually a function of two variables, okay? T and omega. T is time and omega is the sample point. Now this T omega is coming from, T is coming from this close 0 to open infinity, omega small omega is coming from capital omega. Okay, so therefore this order pair is coming from this cross product, Cartesian product of this thing. And on this set one can consider a sigma algebra. I need to fix a sigma algebra to talk about measurability, correct? So that sigma algebra we are taking that on 0 to infinity, here say Borel sigma algebra, and on omega we have already default choice of f. Okay, and then if we take Cartesian product, so Cartesian product of sigma algebra is not a sigma algebra, correct? However, there is a notion called product sigma algebra. Okay, one can come up with a product sigma algebra. So there are many different ways to do that actually. However, we are going to take the approach for which this becomes saturated, okay, or the Cartesian extension way, that I mean in a manner so that this product sigma algebra, okay, would not have any non-measurable null sets. Okay, I mean would include all subsets of null sets. And on the range set I have R here, the Borel's sigma algebra on R. So this is the meaning of measurable space of process if X satisfies this condition, that when in the domain we have this sigma algebra and on the codomain we have Borel sigma algebra, and still this map is measurable, then we call X is a measurable process. However, there is other notions of measurability properties of X. This is called progressively measurable. Okay, so what is progressively measurable? That here we really take care of at time t, okay, over time t, how that xt is having measurability, because in the first case on the left hand side you just had the sigma algebra together, okay, where time t does not play any role. Here we take that process X restricted to interval 0 to t. Okay, so when you restrict to 0 to t, then it is a process on 0 to t. Okay, so we think that t is the terminal time, and then my time domain becomes closed interval 0 to t, and then this space omega remains the same, and then the sigma algebra on this product space we consider this b 0 to t product sigma algebra ft. I mean the same thing actually, the notation is different but it's the same thing I want to mean, and here RBR. So this is measurable for all t. Okay, so if you put this condition, then of course that if we ask that, okay, not the joint thing, but just for t fixed with this omega, the measurability is xt is ft measurable. Yeah, that is trivially true from here. Okay, so here this is progressively measurable process. Now we would also revisit one notion of equal in law, when two processes would be called equal in law. So earlier what we have seen that two processes are modification to each other or indistinguishability. For that necessarily we want both the processes to be defined on the same probability space, otherwise we cannot talk about it. However, there are situations when two processes are coming from two different probability spaces, but still we can we know that, okay, they are similar. I mean they have similar distribution, they behave similarly. Okay, so to talk about it, what we do is that we consider, I mean we cannot consider another omega here because they are coming from two different spaces possibly, but we can of course talk about the time points. So t1, t2, tn. Okay, and at the same time points we observe x1, x2, xn and y1, y2, yn. We can observe them, the value, the range value of the processes, and then we ask if the probability that the joint event xti is in ai for I is equal to 1 to n. Okay, so here that means I am saying that xt1, xt2, etc., xtn, this tuple, this n tuple is in the Cartesian product of a1 cross a2 cross etc. n, and this probability and checking the whether that is matching with the probability that yt1 belongs to a1, yt2 belongs to a2, etc., ytn belongs to an. That means the tuple y1, y2, ytn, this n tuple is in the Cartesian product a1 cross a2 cross etc. an. If that is true, no matter what n you choose, finite n, and no matter what time point you choose, okay, all the time it happens, then you say that okay, x and y have same finite dimensional distributions. And then from the Kolmogorov extension theorem, which I am not going to restate here, I assume that background. So implies that x and y would have the same law. They have the same law. So we would say that okay, they have the same distribution or same law.